Mr. Chairman, dear colleagues, the title of my presentation is Phase Relations in the Systems Based on Cerium Oxide with Oxides of Rare Earth Elements at 1500 Celsius degrees. Oxides of rare earth elements are considerable interest, both from scientific and practical viewpoints, because of their unique structural and functional properties, fire resistance, resistance to corrosion, high thermomechanical and electrical characteristics. Materials based on solid solutions of rare earth oxide are used in electronics, optoelectronics, nuclear and laser technologies, mechanical engineering, chemical industry, metallurgy, medicine, etc. Compounds based on lanthanide oxides are used to produce laser and other optically active elements and optoelectronics. Phase diagrams of CeO2, Lanthan-2O3 and Lanthanide-2O3 systems serve as a physicochemical basis for design of materials for solid electrolytes in fuel cells, oxygen sensors, catalysts, carriers, protective coating on alloys, etc. With this presentation, I would like to offer the overview of our recent results in the binary CeO2, Lanthanoide-2O3 and CeO2, Lanthan-2O3 and Lanthanoide-2O3 ternary systems. Phase equilibria and structure transformations in the system based on the cerium and ytterbium oxides have been studied in air within the temperature range 1500 600 Celsius degrees in the full concentration range using X-ray diffraction analysis and petrography methods. It was established that the system is characterized by the formation of solid solutions in the basis of cubic modification of ytterbium-2O3 C-type and fluoride cerium-2O2 F-type separated by two-phase F plus C region. The systematic study that covered whole composition range excluded formation of new phases. The F cerium-O2 lattice perimeter decreases from A equals 0.5409 nanometers for pure cerium-O2 to A equals to 0.5356 nanometers for the sample containing 25 mole% of ytterbium-2O3 for 1500 Celsius degrees and to A equals to 0.5385 nanometers for the sample with 10 mole% for ytterbium-2O3 annealed at 1250 and 1100 and 600 Celsius degrees. Solubility of ceria in C-type ytterbia decreases from 12 to about 2.5 mole% of cerium-O2 with decreasing temperature at 1500 and 600 Celsius degrees respectively. The slide shows a binary system based on cerium and erbium oxides. The study of solid-state reaction of cerium oxide with erbia at temperatures 600 to 1500 Celsius degrees showed that in this system two types of solid solutions were coexisted: cubic symmetry based on fluoride F cerium-O2 and cubic one C-type erbia oxide, which separated by two-phase field. Dissolution of erbia in ceria during annealing in air proceeds by mutual diffusion and solid solution formation through different valence substitution. Erbium 3 plus ions substitute for cerium 4 plus ions in the F-type lattice sites. In order to preserve charge neutrality of the crystal, the difference in ion charge is compensated by the appearance of oxygen vacancies in sites of oxygen ions. Thus, the F CeO2 lattice parameter reduces for figures 2 and 3, owing to the difference in the cation sizes on the one hand and the sizes of oxygen ion and oxygen vacancy on the other hand. There are, however, such solubility limit values which correspond to a criminal concentration of vacancies beyond of which the fluoride type lattice becomes unstable and transforms into another cubic lattice C-type, characteristic of solid solution of the C-type on the basis of rare earth oxides in the solubility limit increases with temperature rising. The next system is based on cerium and dysprosium oxides. This system is characterized by an almost symmetrical structure, which is due to the close proximity of the ionic radii of the starting components. When the ionic radius of the lanthanide decreases, a narrowing of the phase fields formed in the presented system is observed. The phase equilibria in the system based on cerium and holmium oxides have a similar structure to the systems discussed above. The microstructures of the samples which characterize the two-phase region contain two distinct structural components that are clearly distinguished by contrast. The light phase belongs to a cubic solid solution of the C-type, while the dark phase belongs to a cubic solid solution with a fluoride type structure. The next series of systems investigated in this study are based on lanthanum and lanthanide oxides. It has been found that the system based on lanthanum and holmium oxides is characterized by the formation of three types of solid solutions. These include a solid solution based on the hexagonal A modification of lanthanum oxide, solid solutions based on the monoclinic modification of lanthanide oxides, and cubic solid solutions of the C-type. As the temperature decreases from 1500 to 1100 Celsius degrees, the homogeneity regions of these solid solutions narrow. The parameters of the elementary cells of the hexagonal solid solution A lanthanum 2O3 decrease due to the substitution of lanthanum ions with smaller ions. The next system has a similar structure to the systems discussed above, although it exhibits some differences. In this particular system, a narrowing of the homogeneity region of the hexagonal solid solution based on lanthanum oxide is observed. The slide presents diffraction patterns of samples that characterize all the phase regions formed in this system. This slide presents a system based on lanthanum and erbium oxides. The structure of this system becomes more complex due to the formation of an ordered phase with a perovskite-like structure. The homogeneity range of this phase extends from 45 to 51 mol% erbium 2O3. The microstructure of the sample containing 40 mol% of lanthanum 2O3 and 60 mol% of erbium 2O3 is characterized by pleochroism, which is a property of anisotropic crystals to change their color depending on the direction of the light waves passing through them. This phenomenon is associated with the fact that in anisotropic crystals the degree of absorption of different wavelengths of visible light depends not only on the chemical composition of the crystal, as in isotropic crystals, but also on the orientation of the light beam relative to the optical axis of the crystal. Thus, if this is In this microstructure, the formation of isotopic crystals of the light phase belonging to C-erbium-2O3 and anisotropic gray phase with different shades due to the effect described above, belonging to the ordered phase with a perovskite-like structure is observed. This slide shows an isothermal section of the ternary system based on cerium, lanthanum, and dysprosium oxides. In this system, homogeneity regions are formed based on the hexagonal solid solution of lanthanum oxide, cubic solid solution with a fluoride type structure, cubic solid solution of the C-type, as well as a homogeneity region based on the monoclinic modification of lanthanide oxides. The isothermal section is characterized by the formation of two three-phase regions. The microstructure of the three-phase sample is characterized by the presence of three structural components that differ in contrast and morphology. The rod-like phase corresponds to a hexagonal structure. The light phase has been identified as a monoclinic solid solution of lanthanide oxides. The dark phase belongs to a cubic solid solution with a fluoride type structure. The next slide shows an isothermal section of the ternary phase diagram of the system based on cerium, lanthanum, and holmium oxides. This isothermal section is characterized by an enlargement of the homogeneity region of cubic solid solutions of the C-type. At the same time, there is a narrowing of the homogeneity region based on the hexagonal modification of lanthanum oxide. The microstructure of the two-phase sample containing a hexagonal solid solution and a solid solution based on a cubic fluoride type structure is characterized by two structural components that differ in morphology. The rod-like phase belongs to the hexagonal solid solutions based on lanthanum oxide. The other structural component belongs to a cubic solid solution with a fluoride-typed structure. The structure of the isothermal section of the ternary system based on cerium, lanthanum, and erbium oxides differs from the previously discussed systems due to the formation of an ordered phase with a perovskite-like structure. As the ionic radius of the lanthanide decreases, there is an increase in the homogeneity region based on cubic solid solutions of the C-type. The slide shows an isothermal section of the ternary system based on cerium, lanthanum, and ytterbium oxides. It is established that in the ternary system, cerium O2, lanthanum 2O3, ytterbium 2O3, fields of solid solutions based on cubic F modification of the structure of fluoride, cerium 2O2, monoclinic B and cubic C modification of ytterbium 2O3, and hexagonal A modification of lanthanum 2O3 with perovskite type structure of lanthanum erbium O3R with rhombic distortions. It was found that the rare fraction of cerium O2 in the crystal lattice of the ordered phase with the structure of the perovskite type lanthanum erbium O3 is about 3 mol. The isothermal section of the cerium O2, lanthanum 2O3, and ytterbium 2O3 system at 1500 Celsius degrees contains 4 2-3-phase F plus C plus air, then A plus air plus F, and 5 two-phase regions A plus F, A plus air, air plus C, F plus air, and F plus C. The microstructures of samples characterizing different phase regions are shown on this slide. Thank you for your attention, and I would like to express my gratitude to the organizers of the competitions for honoring me with the Best Researcher Award. Thank you.